Welcome to this lecture number 39 on this NPTEL course on fluid mechanics for undergraduate chemical engineering students. The topic that we are discussing currently is turbulent flows, and we discussed in the last lecture, lecture number 38, that turbulent flows are characterized by a large amount of fluctuations about the mean. Suppose you consider a flow in a pipe, okay, and let us say this is z direction of the flow and r is the direction normal to the flow, the radial direction along the pipe. Okay. So, while there will be mean flow, if you apply a pressure drop between the ends of the pipe, while there will be a mean flow in the z direction, there will also be a large amount of fluctuations about this mean flow. And if you measure, for example, the z velocity as a function of time using some probe at a given point in space in the pipe, you will find that there will be a large amount of fluctuations about the mean. Okay. While if you measure the so this is the 0 of the, so this is the z component of the velocity, while on the other hand, if you measure the r component, there will again be fluctuations, but they will be fluctuating about the 0 because there is no net flow in the r direction. The pressure gradient is only along the z direction, therefore, there will be flow only along the z direction. Okay. So, the fluctuations that are present in a turbulent flow play a very key role in determining the stresses that are present in a turbulent flow. Now, so we decided that it is better to restrict ourselves to predicting the mean quantities such as the time average quantities, velocities, etc., because from an engineering perspective, from the point of view of practical applications, what we want is actually average quantities such as friction factor or volumetric flow rate or pressure drop and so on. So, these are all average quantities. So, it makes sense for us to restrict ourselves to predicting only the mean rather than the fluctuations. Okay. But as we saw in the last lecture, and as I am going to reiterate that point again, the fluctuations do play an indirect role even in determining the mean. Okay. And the way that happens is like this. Okay. You write the total velocity as a mean plus fluctuations. Fluctuations are denoted by prime. The mean velocity is defined as 1 over t in the limit t tending to infinity 1 over 2 t times integral t minus t to t plus t v z of t prime dt prime. What we are essentially saying is here is that suppose you look at this velocity profile, this velocity data, let us say this is the actual velocity data. Now, we are going to take some time t, okay, and we are going to integrate the velocity fluctuations in this region between minus t and plus t, that is t minus tau to t plus tau, okay, and we are going to integrate this data, okay, and divide by 2t. Okay. Now, if the flow is steady in the mean, that is if the flow is stationary, that would imply that V z itself is independent of time. What this means is that you could have you could imagine doing this averaging by shifting this t to some other value. Let us say here you could also have t here and then do from t minus t to t plus t, small t minus capital T to t plus capital T, and the averages thus computed will be independent of where you choose t to be. That is the meaning of stationary flows or steady in the mean, okay, flows. So, what we did was to substitute this split V z is a function of x, y, z time, this V z bar. V z bar is already time average. So, it is a function only of x z, x y z plus V z prime, which is a function of x y z and time, back in the Navier-Stokes equation. Okay. And we average the entire Navier-Stokes equation. While doing so, we neglected quantities such as like this V y prime dV x bar dy bar, okay, whole average. This would be essentially V y prime average times dV x bar by dy although this is non-zero, okay, but the average of a fluctuating quantity is 0. Okay. So, such quantities which occur as which occur linearly in fluctuating quantities when substituting this expansion, the total flow is the mean plus fluctuations back into the Navier-Stokes equation. You will encounter quantities like this, and those are 0, but we will also encounter quantities such as this, the product of two fluctuations average, and this is not 0. Okay. The product of two fluctuations is the average of product of two fluctuations is not equal to the product of their averages, and this is because of the fact that these two quantities could be correlated in time. So, when you integrate over a particular extent of time, they could in general be non-zero. So, the integral could be non-zero, although the individual values, if you integrate over time, could be 0, because if they are positively correlated, then they could be non-zero. So, that is the main reason why fluctuations play a role even in determining the mean turbulent flow. Okay. Okay. So, now after substituting all this and time averaging, we finally ended up with this expression rho dVx dx plus Vy dVx dy. This is the most general expression. We are of course going to simplify this little later for specific cases. X dz, okay, is equal to minus p partial x plus partial tau x x bar by partial x plus partial tau y x bar partial y plus partial tau z x bar by partial z, plus if you merely put bars in the Navier-Stokes equation, the steady Navier-Stokes equation, you will just get this, but the fluctuations play a role because there are quantities such as this, okay, minus d dx of rho V x prime bar minus d dx of rho okay, d dx of rho V y d dy of rho V y prime V x prime bar minus d d see there is a minus sign. So, that is correct, minus d d z of rho V z prime V x prime. Now, these three, okay, so can be again included back into this derivative, minus partial p bar by partial x plus partial by partial x of tau x x bar minus rho V x prime plus partial by partial y of tau y x bar minus rho V y prime V x prime plus partial by partial z of tau z x bar minus rho V z prime V x prime whole bar. Okay. Now, these are termed as Reynolds stresses because they appear as stresses and they appear in the same way as the viscous stresses appear, divergence of the viscous stress. These are called turbulent stresses or Reynolds stresses. So, this is for example denoted as tau x x turbulent, this is denoted as tau y x turbulent, and this is denoted as tau z x turbulent. Okay. These are called Reynolds stresses. Or simply turbulent stresses. So, they are denoted as some tau x y turbulent and so on. They are also symmetric tensors, they are also tau x y is tau y x, they are symmetric, okay, but their origin lies purely in the fluctuating motion that is present often in a turbulent flow. Okay. Turbulent flows are often characterized by rapid random fluctuations in both space and time. So, these are basically averages of quantities, products of quantities, and they are in general time dependent. Okay. Now, we have to solve this, but in order to solve this we have to tell something more about these turbulent stresses. So, one option is to write the turbulent stress in terms of a viscosity called eddy viscosity times the mean velocity gradients, just as we wrote for the viscous stress. Okay. This is called the eddy viscosity hypothesis. This is not a rigorous relation, this is merely a hypothesis. Okay. So, this is called the eddy viscosity hypothesis. Now, if eddy viscosity, which has the same dimensions as the normal viscosity, if this is a constant, then it is a trivial addition, because it changes nothing. It is almost like you are increasing the effective viscosity by eta plus eta eddy. Okay. So, it will be another viscosity. So, we are merely changing the character of the fluid by increasing its viscosity by a tiny amount, by some amount. But so, this is not what is happening in reality, because this eddy viscosity is not a constant, it is a function of spatial positions in general. Because for the simple reason that if you consider turbulent flow past a solid surface like turbulent flow in a pipe, near the wall at the wall itself the velocities are 0 by no slip condition and no penetration condition. So, near the wall the velocity fluctuations will be small compared to the bulk of the flow. So, near the wall the magnitude of the fluctuations are small. So, therefore, the turbulent stresses will be small, and hence since we are trying to model the turbulent stress in terms of the mean velocity gradients, somehow the eddy viscosity has to be small in order to keep the turbulent stresses small close to the solid surface. So, that physical aspect has to be built in the model by saying that eddy viscosity is not a constant, but instead it is a function of spatial positions. Okay. So, in some sense what we are trying to do in this type of hypothesis or in this kind of modeling is that our ignorance about the way in which turbulence transports momentum is sort of buried in this single parameter. So, one can often ask the question whether a single parameter, well, it is not a single constant parameter, it is a function, but whether a single function can alone describe all the complexities of turbulence. So, that is a fair criticism, but nonetheless for engineering applications we will show that the eddy viscosity proves a very reasonable tool to predict for example, friction factor versus Reynolds number relation in the turbulent regime. With some suitable physically motivated approximations and with some experimental input, we will show a little later that we will predict using this model. So, we will be content in this course by using the eddy viscosity like approach, although it has its own limitations, okay, in terms of generalizing how this approach can be extended to other turbulent flows, but at least for turbulent flow through tubes and rectangular channels and turbulent flow past a flat plate, all these kinds of turbulent shear flows, it turns out that the eddy viscosity is a fairly reasonable model, especially if you are interested in engineering applications. Okay. Now, so as I told you, the eddy viscosity has to be in some sense we have to provide a model for eddy viscosity, otherwise it is not a constant that we have agreed. So, the model for eddy viscosity was first provided by Parental, it is called the Parental mixing length model. So, Parental wrote an expression for eddy viscosity like this, times the rho times L squared, where L is called the mixing length, okay. Rho is the density of the fluid, and this is the magnitude of the velocity gradient in the fluid. Okay. This is the Parental's eddy mixing length hypothesis for eddy viscosity. Now, the origin of this expression comes from kinetic theory of gases, wherein if you consider the normal viscosity, the routine shear viscosity of a liquid, okay, the dynamic viscosity of a liquid, one can use for if you consider the kinetic dynamic viscosity of a dilute gas such as air using kinetic theory, you can write down the viscosity in terms of the density of molecules times the mean free path squared times the velocity gradient, the magnitude of the velocity gradient. In a similar spirit, Parental wrote down this. He imagined that instead of molecules, you have these turbulent eddies which are undergoing this random motion, and therefore, these eddies are able to transport momentum just as molecular collisions transport momentum in a dilute gas. This is a hypothesis that the turbulent eddies almost act in a similar manner. So, he wrote an expression based on this mixing length. Okay. So, the mixing length is physically the length over which a turbulent eddy loses its identity, just as what is the mean free path in the classical kinetic theory is the distance, typical distance between two collisions of between two molecules. In some sense, a turbulent eddy moves, okay, and then once it collides with some other eddy, it sort of loses its identity. So, turbulent eddies themselves are rough or loose concepts, they are not rigorous concepts like velocity and vorticity, but these are physical concepts which are motivated by intuitive ideas rather than rigorous first principles. Okay. So, key thing is that at the wall, okay, if you have any turbulent shear flow at the wall, there has to be some non-zero velocity gradient. So, the velocity gradient is not 0 at the wall, but you would expect the turbulent fluctuations to go to 0 at the wall. Therefore, eta eddy has to go to 0 at the wall. If this is not 0 and if this is not 0, rho is the density of the fluid, cannot be 0. So, L has to somehow go to 0 at the wall, at solid walls, at rigid surfaces. Okay. So, this is something that we can say very in a very definitive way from straightforward physical considerations, that at a solid surface the eddy viscosity has to go to 0, because otherwise if it does not go to 0, the turbulent fluctuations, the turbulent stresses will not go to 0, but if the eddy viscosity is 0, that means that we have to somehow say that this mixing length has to go to 0. So, the mixing length is in fact, so instead of saying in some sense what we have done is to trade one unknown function to another unknown function, because everything else is known in the problem. Okay. But this model does have some physical grounding in the sense that it is motivated by kinetic theory of gases, where random motion of molecules and collisions transport momentum. Here we are making an analogy by saying that the random motion of eddies in a turbulent flow transports momentum. Okay. Now, we are going to go to a specific example, turbulent pipe flow. We have already seen that turbulent pipe flow can be characterized using experiments in terms of the friction factor versus Reynolds number chart, and in the laminar regime we know the exact analytical relation by solving the Navier-Stokes equation under simplifying assumptions. Now, can we make some progress in predicting the friction factor versus Reynolds number relation in the turbulent regime using the eddy viscosity kind of approach? Okay, that is a question we want to answer. Now, of course, turbulent flow in a pipe must be addressed in cylindrical coordinates. So, I will switch to cylindrical coordinates. So, the mean flow will satisfy, there is only one mean flow V z. Okay. So, V r is 0 and V theta is 0. Okay. So, many terms will drop out. So, the mean flow is in the z momentum equation, okay, is plus 1 over r d d r of r d tau r z by d r. Well, but we also have not just this, we also have the turbulent contribution. So, let us write this as there are both the mean viscous contribution plus the turbulent contribution. Okay. So, in some sense we can rewrite this very simply to yield T r z plus T r z T is nothing but, so we can write is equal to d p d z. Okay. And then we take r here and then integrate, you will get tau r z plus tau r z t is d p d z times r squared by 2. So, this is d d r of r. So, you will have an r after integration plus some constant. Okay. So, tau r z bar plus tau r z turbulent is d p d z r by 2 plus C 1 by r. Now, we can readily say that as r goes to 0 in the center of the pipe, the stresses will be finite. So, C 1 has to go to 0. So, we can say very easily that tau r z plus tau r z turbulent is r by 2 dp dz. Okay. Now, if we do a macroscopic momentum balance, so you take a tiny section of the pipe delta z, do a macroscopic momentum balance, the forces here are the pressure forces on this side and this side. If you take this as the control volume, now and on the surface you will have viscous forces which will retard the fluid in the minus z direction. Okay. So, you have dp dz times delta z is equal to the stress, wall shear stress exerted by the wall on the fluid times 2 pi r delta z, okay, where r is the radius of the pipe. Okay. Now, you can easily see that delta z will cancel, 1 pi will cancel and 1 r will cancel to give tau w is nothing but, okay, r times minus dp dz by 2. Okay. So, we substitute instead of dp dz instead. So, this implies minus dp dz is 2 tau w by r. We substitute this term out here, okay, to give, okay, to get tau r z plus tau r z turbulent is, okay, minus r by r tau w, because that is what it is. You have plus dp dz here, you have minus dp z here. So, if you substitute in terms of tau w, the wall shear stress, you will get simply minus r, the factors of 2 will go away. Okay. Now, we know what is tau r z, okay, this is eta times T r, and we know what is the turbulent stress in the r z direction, that is from the mixing length model. Okay, it is rho L squared times dvz dr times dvz dr, okay, is equal to minus r by r tau w, the wall shear stress exerted by the wall on the fluid. Okay. Now, so you have a pipe, okay, the axis is along the center of the pipe. So, we said that r is along this direction, z is along this direction. Now, I am going to define y from the wall towards the center. So, trivially r capital R minus small r is equal to y. This implies dy is minus dr. So, once I use this, and I can convert this entire equation in terms of, y, okay, which I will do very quickly. Okay. So, you will have rho L squared, okay, times d v z by dy whole squared plus eta dv z by dy minus 1 minus y by r times tau w is 0. Okay. Now, notice that y is going like this and the velocity profile will be like this. So, dv z dy is a quantity that is positive, okay, and okay, that has been taken into account in R. So, the mod is not required anymore, because the dv z dy is positive. Now, the boundary condition is that v z bar is 0 at r equals capital R. There is a no slip condition, which is satisfied by both the mean and fluctuations. So far we have not specified what is L as a function of y. So, we have to specify this, okay. That is another task that we have to do. Okay. So, before I proceed further, I am going to non dimensionalize this using turbulence scales. These are done conventionally. The scales used for non dimensionalizing are not very obvious. The velocities are scaled by the friction velocity, which is denoted as u star, that is nothing but square root of tau w by rho. Okay. So, but we know what is tau w in terms of the macroscopic momentum balance. Tau w is r by 2 delta p by L. So, that is something that we just derived using a macroscopic momentum balance here. So, this expression. So, instead of dp dz, I am going to write delta p minus dp dz, I am going to write delta p by L. So, delta p by L is minus, okay. That is pressure at the inlet, delta p is nothing but p inlet minus p outlet. Okay. So, that is the definition of delta p. So, u star therefore becomes square root of r by 2 delta p by L 1 over rho within the square root. Okay. Now, we know that delta p by L is related to friction factor for flow in a pipe. Okay. So, here I am going to use the fanning friction factor, which is differs by a factor of 4 from the Darcy friction factor, which we have already pointed out the differences. Fanning friction factor is defined as delta p divided by 2 rho v squared, okay, times d by L is equal to F. Okay. This is the fanning friction factor. Now, there are two types of averages that are involved. Suppose I have a quantity, okay, V z, the over bar denotes time average, the angular brackets denotes cross sectional average. Remember that when we define friction factors, okay, we have to define with respect to a cross sectional average velocity, but here we are considering turbulent flow. The velocity is also time dependent in general, but we are worried only about the time independent mean flow. So, there is an average with respect to space as well as a time period, okay, the extent of time. Okay. So, using this I can write what is delta p by L in terms of F, and I can substitute it back here. Okay. So, I will get u star, the scale used for non dimensionalization is nothing but square root of delta p by L d by 4 1 over rho, but delta p by L times d by 2 rho is F times v squared. Okay. So, delta p by L d by 4 rho is nothing but F by 2 v z. Okay. So, v z squared. Okay. So, if you substitute this in here, you will get u star is v z average square root of F by 2. So, this is a highly non trivial velocity scale. This is called the friction velocity, because normally we would non dimensionalize things only by this. Here we are trying to multiply it by a square root of F over 2. So, it is highly non trivial in terms of non dimensionalizing turbulent flow. So, we will define the non dimensional z velocity as u by u star, and we will define non dimensional distance y plus as y by nu by u star, where nu is eta by rho is the kinematic viscosity. Okay. So, since we have used the length scale for non dimensionalization is this, not the radius of the tube, and there is a very important reason why we are choosing a different length scale. This length scale is not set by the macroscopic dimensions of the geometry such as pipe radius or channel width or length of a plate or something. It is inherent to the turbulent flow, because nu is the kinematic viscosity and u star is essentially friction velocity dictated by the turbulent flow. Okay. So, the non dimensional radius, okay, will become r plus is r times u star by nu, that becomes R e times square root of f over 8, okay, where R e is defined as eta. Okay. And you also have a non dimensional mixing length, because that also has to be all the length scales has to be non dimensionalized by nu divided by u star. Okay. L plus is L divided by nu by u star. Okay. So, after doing all this, we can rewrite this expression. We have this expression out here. We can rewrite in terms of the non dimensional variables we have just defined. Okay. Okay. So, we will write this as L plus squared du plus by dy plus whole squared plus du plus by dy plus minus 1 minus y plus by r plus is equal to 0. Now, this is a quadratic in du plus by dy plus. So, it is like a quadratic equation. So, you can solve this quadratic for what is du plus by dy plus and so that becomes minus 1 plus square root of 1 plus 4 L plus squared times 1 minus y plus by r plus divided by 2 L plus squared. The reason why we are not choosing the minus root is because we know that du plus by dy plus is a positive quantity, because you notice that y goes from the wall towards the center. So, the velocity profile will increase in some sense like this. So, du plus by dy plus cannot be a negative quantity. If that is the case, then you cannot choose the negative root, because you already have a negative number in the first term. So, the second term better be positive in order to make du plus by dy plus a positive quantity. Okay. So, and we can solve this equation by using the no slip condition. At the wall u plus must be 0. So, we can integrate this equation. Okay. Okay. U plus is integral 0 to y plus minus 1 plus square root of 1 plus 4 L plus squared 1 minus y plus by r plus, okay, divided by 2 L plus squared times dy plus. Okay. Now, this is by integrating from the wall towards the center. Another way of integrating is, which is also often useful, is to integrate from the center line, that is from r plus towards the wall. Okay. So, this is by integrating from y plus equal to 0 to any y plus, but we can also integrate from y plus is r plus to any y plus. Okay. So, once we do that, we will get u plus is u plus max plus integral y plus to r plus 1 minus square root of 1 plus 4 L plus squared times 1 minus y plus by r plus divided by 2 L plus squared dy plus. Okay. So, this is also possible. So, we will find use for both these expressions in our discussion to follow. Now, Parental proposed for the mixing layer, length, a hypothesis for the mixing length. See, the mixing length has to go to 0 at the wall. So, the simplest hypothesis is that it is some constant k times y plus. It is a linear function of y plus, and experimentally it turns out that k works to be 0.4 to predict the friction factor. We will come to that a little later, but right now we will just treat k to be a constant, which can be fitted by comparing with experiments. Okay. So, once we do that, if you look at this expression, so let us rewrite this expression again. I am going to rewrite this expression again and make an important observation. So, what we are going to do is to use this expression where we had u plus as integral 0 to y plus times minus 1 plus square root under 1 plus 4 L plus squared times 1 minus y plus by r plus divided by 2 L plus squared times dy plus. So, we are going to use this expression to analyze some and draw some very important conclusions about turbulent flow past solid surfaces. The first thing is universality. Okay. Now, if you look at this expression, the only way in which radius enters the problem is through this term. Okay. So, 1 minus y plus by r plus. If y plus by r plus is small compared to 1, that is if you are fairly close to the wall, okay, then we can treat 1 minus y plus by r plus as approximately 1, and therefore, all the dependence on the radius end of the pipe, okay, disappears from the problem. So, essentially you have u plus as a function of y plus as approximately for under this condition that y plus by r plus small compared to 1, that this is approximately equal to okay, minus 1 plus square root of 1 plus 4 L plus squared divided by 2 L plus squared times dy plus, okay, or you can simplify this further. Okay, we can write root of 1 plus 4 L plus squared minus 1, okay, as, okay, suppose you consider root of 1 plus 4 L plus squared minus 1 times root of 1 plus 4 L plus squared plus 1 divided by root of 1 plus 4 L plus squared plus 1. I am multiplying and dividing by the same quantity. This is of the form, so if I multiply these two terms, I get 1 plus 4 L plus squared minus 1 divided by square root of 1 plus 4 L plus squared plus 1. Now, the two minus 1's cancel to give you 4 L plus squared by square root of 1 plus 4 L plus squared plus 1. So, essentially I can write therefore, that if I were to have this term, I can replace this by this term here which we derived, okay, 4 L plus squared by root of 1 plus 4 L plus square plus 1, this entire thing. This 4 L plus squared will cancel with 2 L plus squared to give you only a factor of 2. So, u plus as a function of y plus becomes twice 0 to y plus, okay, dy plus divided by 1 plus square root of 1 plus 4 L plus squared. Okay. Now, if you look at this expression has no radius of the pipe in it, and there is no reference to the geometry of the pipe also, it is fairly close to the wall. So, this equation must be true for any turbulent flow past a rigid surface, turbulent shear flow past a rigid surface, be it flow through a pipe or flow through a rectangular channel or flow past a boundary layer, flow past a flat plate. As long as the flow is turbulent and the flow is in one direction, okay, predominantly in one direction, these are called turbulent shear flows, then this is in fact true. So, this is a universal velocity profile close to the wall. So, all turbulent shear flows close to the wall must exhibit this universal velocity profile. Now, if you are very close to the wall, so we remember that Parental's hypothesis is L plus is k y plus. Okay. If you are very close to the wall, okay, so you will have L plus and k is about 0.4. Okay. If L plus is much small compared to 1, or we can say that y plus is small compared to 10, okay, it is 1 over 0.4, okay, it is about 10, then so k is 0.4. So, it is about if k y plus is small compared to 10, then you will have 1 plus 4 L plus squared, you can be treated approximately as 1. Okay. So, 1 plus 4 L plus squared is, because L plus is very small compared to 1, you can do that. So, you will have u of y plus is approximately 0 to y plus 1 plus order L plus squared times dy plus, or you can say that u of y plus is approximately y plus close to the wall. Okay. So, this expression is in fact obtained, if you go back to our original differential equation, okay, if you go back to the original differential equation, here this expression is obtained by neglecting, this is the contribution due to eddy viscosity, this is the contribution due to the shear viscosity, normal viscosity, this is neglected close to the wall, because close to the wall the turbulent fluctuations are small, turbulent stresses are small, that is what we mean by saying L plus is small compared to 1. So, this term wins over this term and this term balances this term, again this is small, y plus is small compared to. So, when du plus by dy plus is 1, that means that the velocity profile is linear. So, this region close to the wall is called the viscous sublayer. Okay. Sometimes the term laminar sublayer is used, but the flow is of course not laminar in this region, it is in fact turbulent, but the viscous effects dominate the turbulent stresses very close to the wall, and this is a very universal feature of any turbulent shear flow past a solid surface. This is not restricted to flow in a pipe, turbulent flow in a pipe. Okay. So, let us look at turbulent core, that is in the center of the pipe. Can we say anything more general? Okay. So, we are far away from the wall. Okay. So, you have L plus large compared to 1, because L plus is k y, remember k y plus, and y plus is large compared to 10, okay. But still we are saying y plus is less than r plus. Okay. So, remember the other expression we had for u plus in terms of, by integrating from the center of the pipe, u plus max, the maximum velocity, plus y plus to r plus 1 minus square root of 1 plus 4 L plus squared times 1 minus y plus by r plus dy plus divided by 2 L plus squared. Okay. Now, if L plus is large compared to 1, okay, so you can say 1 minus square root of 1 plus 4 L plus squared times 1 minus y plus by r plus is approximately, okay, is equal to 2 L plus times 1 minus y plus by r plus whole to the half. Okay. If L plus is large compared to 1, then we can say that this is approximately just equal to this. Okay. Now, so we can further therefore write u plus as u plus max minus integral y plus to r plus 1 minus y plus by r plus to the power half dy plus divided by L plus. Okay. Now, L plus is k y plus, this is the Parental's hypothesis for the mixing length being a function of the distance from the wall. So, u plus is nothing but u plus max minus integral y plus r plus times 1 minus y plus by r plus to the power half by k y plus dy plus. Okay. So, all we are saying is that when L plus is large compared to 1, okay, we are expanding this term, okay, and that is the only simplification that we are making. Okay, when we do this whole exercise, that is the only simplification we are making. Okay. Now, if you look at this expression, okay, you can integrate this, u plus is u plus max plus 2 by that constant k times root of 1 minus y plus by r plus 1 over k logarithm of 1 minus square root of 1 minus y plus by r plus by 1 plus square root of 1 minus y plus by r plus. Okay. Now, here there are only two constants that are floating around, u plus max and k. Okay. Now, k should be independent of flow conditions, because we have shown that it is the mixing length. So, it should not be a function of the flow, okay. It could be a function of geometry, for example, this is pipe flow, but generally it should not be a function of flow conditions, but u plus max is a function of flow conditions, because that is the maximum flow velocity of the pipe, not in a non dimensional sense. Okay. Suppose you have y plus by r plus less than 0.5, you can expand the square roots. So, root of 1 minus y plus by r plus is approximately 1 minus half y plus by r plus so on. Okay. So, when I substitute this back out here, you get u plus is 1 over k, okay, ln y plus 2 over k minus 1 over k ln 4 r plus u plus max plus order of y plus by r plus. So, we are not close to the center line, but at the same time we are far away from the wall. Okay. This is called the turbulent core region, okay. And experiments tell you that u plus is 2.5 ln y plus, okay, plus 5.5. So, by comparing these two expressions, we can infer, this implies that k is 0.4, okay, and u plus max is 2.5 logarithm of re root f plus 1.37. Okay. So, this is the description that we have, okay, for the flow that is far away from the wall, but still little away from not close to the center, but little away from the center. This is called the turbulent core region. So, we have a description for very close to the wall, we have the viscous sublayer, where the velocity profile is just proportional to y plus, and then we have a logarithmic velocity profile far away from the wall. Okay. So, we can patch these two relations. So, we have these two relations, u plus is y plus the viscous sublayer, and we have u plus is 2.5 log y plus 5.5. Now, if you plot these two curves and then say that the region where these two curves meet is the thickness of the viscous sublayer, then so you will have u plus as a function of log y plus, you will have one asymptote like this, another asymptote like this. So, if you equate these two and say this is the viscous sublayer thickness, then you will find that delta V s plus the thickness of the viscous sublayer, the non dimensional thickness of the viscous sublayer is 2.5 logarithm of delta V s plus 5.5. If you solve this, you will get delta V s plus is 11.6. Okay. So, the non-dimensional viscous sublayer thickness is 11.6 in general. Okay. Now, we have all the required quantities to find the friction factor versus Reynolds number relation. Okay. Now, you know that u star is square root of f by 2 V z. Okay. So, this is nothing but square root of f by 2. The definition of V z is 1 over pi r squared 0 to r 2 pi r, the time average velocity V z bar dr, and this is u star. We know that u plus is V z by u star. Okay. This implies, so I can bring, since u star is a constant, I can bring this u star to the denominator here and then call it u plus, and then I can get a relation for the friction factor 2 by root f is 2 by r squared 0 to r u plus dr. Now, I am going to convert from r to y. Okay. So, this becomes 2 by r squared 0 to r capital R minus y u plus dy. Now, we know that u plus has a composite description. Close to the solid surface you have the viscous sublayer, little away you have the logarithmic region, but as a first approximation if you use u plus is 2.5 log y plus 5.5 in the entire pipe, we are saying that we are not going to account for the viscous sublayer and we are not going to worry about the velocity profile close to the center of the pipe, because this logarithmic velocity profile is valid only in the intermediate regime far away from the wall, but again little away from the center of the pipe. Okay, we are not going as far as the center of the pipe, but as a first approximation if you just use this out here, let us see what happens. Then you will get 1 over root f is 1.8 log R e root f minus 0.6. Okay. But this is the expectation from theory. Experiments show that 1 over root f is 1.7 log R e root f minus 0.4. Okay. So, this is a very approximate model after we made so many approximations yielded this, while experiments show this. Okay. So, that shows, this gives some confidence in the efforts that we have made in understanding the turbulent flow in a pipe, because we do get constants that are fairly close to experiments. Of course, we have to correct them, but that is understandable because we have made a whole lot of assumptions and we have made errors in actually extending the velocity profile all the way from the wall to the center, the logarithmic velocity profile, when in reality it is not valid. So, we have made several approximations, but having done all those approximations, it is quite satisfactory that the result from this approximate analysis of turbulent flow yields very close results very close to the experimental result. So, this equation is called the von Karman Nikuradse equation, and this predicts reasonably the f versus Re data that we already saw in when we discussed pipe flows and losses, when we discussed friction factor Reynolds number relation. The turbulent flow region for smooth pipes is reasonably captured by this relation, and we also have obtained a reasonable understanding of what is going to happen in terms of in detail what is the velocity profile and why it is changing using a simple mixing length hypothesis due to Parental. Okay. We will stop here and at this point, and in the next lecture, lecture number 40, we will try to summarize everything what we have done in this course, and also list out what is ahead in terms of what are the newer things that we could not have time to go through, but which are essentially very important, but we could not cover them for lack of time and lack of scope of this course. So, we will stop here and we will meet again in the next lecture.